Okay, this is the second lecture in our logic discussion. So we just finished making a data frame. We had two columns, age and time on the game. And we did cbind, which assigned it to this variable game_user. And then we converted that using this as.data.frame function to make sure that it was a data frame. We checked the structure and it is a data frame. We viewed it and we see it here. Okay, so it has two variables in it, age and time on the game. So if I do this, game_user, that's the name of the data frame, $age, I should see the age variable or the age variable or the age vector. Okay, so it's 19, 18, 20, 19, 21. These are the ages of the students in our data frame. We can see that this is a vector. So what happens when we do something like this? We say we refer to this vector, and then we put this symbol here, which is, I guess, less than or greater than, I'm not sure what I call it, and then 20. I guess it's less than, and 20. So what is this going to do? So what if I do this and I hit return, I get this. So what does this mean? It evaluated this statement for each value in the vector. So is 19 less than 20? True. Is 18 less than 20? True. Is 20 less than 20? False. Is 19 less than 20? True. Is 21 less than 20? False. So we can see that, when we compare this variable to 20, which is what we're doing here, we're comparing it, we're checking is it less than or greater than or equal to 20, using the less than symbol, this symbol here. 20 actually, what happens in R is 20 gets recycled. We used this word before. It means that although 20 looks like it's just a single number or so-called scalar, really in R they say everything is a vector, or there are no scalars. What they mean is that this 20 gets recycled and basically it looks like a vector. It really looks like, what it really becomes is this. It really becomes this. It becomes a vector of 20s. So when we run it, we get that. So it's comparing each element in the age vector with a 20. So that's what recycling means. So 20 gets recycled so that R can compare each value in the age vector to 20. So the result we get is a Boolean, but it's a Boolean vector because we get one for each element in the age variable or the age vector. Okay, so we get a Boolean vector here. This is what we get. So the truth value, these represent the truth values of 5 different statements actually. So the first statement is 19 less than 20? The second statement is 18 less than 20? Is 20 less than 20? Is 19 less than 20? Is 21 less than 20? So these are the truth values for 5 different statements. Okay, next let's talk about compound expressions. We said we wanted to introduce the idea of compound statements, compound expressions. When we were on this slide, we said all of these are statements, and in fact this is also a statement. And okay, so let's look at that. Compound expressions are also statements. So what does that mean? Well, what does something being a statement mean? means that it's either true or false. So we can have a so-called compound expression, and it will also can also be a statement. So this is one expression, just this left side. 6 is less than 7. That happens to be true. And here's another expression, 8 is less than 9. That also happens to be true. But we can make this statement together. Certainly you can make this statement in English. You could say 6 is less than 7 and 8 is less than 9. So you would ask, is that true or false? The whole statement, the whole compound expression. Okay, we can combine statements using connectives, so-called connectives, also called logical operators, like and. So here we used and. We can also use or, like 6 is less than 7 or 8 is less than 9. Also not is a logical connective. So we might just say 6 is not less than 7, or in a more clumsy way, not 6 is less than 7. And also if then. So in English this is kind of doesn't look like a single connective. It looks like maybe it's two, but it's only one, and I'm sure there are languages, maybe in Japanese or other languages, where you might be able to get away with just using one word. You don't need two. Anyway, it's just a single connective. It just happens to be expressed this way in English. Okay, with these here, we derive what are called new compound statements, i.e. the new compound statements are either true or false, but not both. For example, this one, 6 is less than 7 and 9 is less than 8. So this is by itself is true, but this one by itself is not true. And what about this compound statement? If we say 6 is less than 7 and 9 is less than 8, we would say no, that's not true. However, if we wrote this, 6 is less than 7 or 9 is less than 8, that would be true, because or only requires one of them to be true in order for the whole compound expression or statement to be true. Here's another one. If x is divisible by 2, then x is even. So this is also a compound statement, because it has x is divisible by 2 is one statement, which may or may not be true depending on what x is, and x is even is another. Or we would say, in this case, since we're talking about x, we would say this would evaluate to a statement once we give x a value. So if x is equal to 10, then this is a statement. It's either true or not. Is 10 divisible by 2? Yeah, that happens to be true. Is 10 even? That happens to be true. Anyway, once you supply a value of x, then we say it evaluates to a statement. And that statement evaluates to a true-false value. We could also say that. Okay, these three sentences here are also statements, but we'll call them compound statements. Now, I just want to warn you that in Java, the word expression has a particular meaning, and the word statement might have a particular meaning, and it may not be the same as in logic. And also in Python, the same thing. It may or may not be the same as in logic. So just be aware of which context you're speaking of when you use the word statement. Okay, so we just saw that there are these various connectives. I think we named 4 of them. Let's examine them individually. So let's talk about the and, and that's called a conjunction. So and is called a conjunction. In logic, not in R, we conveniently use P, Q, and R to denote statements. Okay, so we might say there's a statement P, there's a statement Q, there's a statement R. It's not necessarily what we do in R, but in logic that's the way things are handled. Any two statements can be joined by the word and to form a compound statement called the conjunction of the original statements. Symbolically, in logic, not in R, we would write something like this. This is not the way we would do it in R. In fact, we already know what this symbol means. In R, this means exponent. So it's not the same. This, in logic, though, denotes the conjunction of the original statements and is read as P and Q. So this is and in logic, but not in R. Let's skip that. Okay, and now let's look at this code, and then we'll actually run it after we just examine it here. But the conjunction symbol in R, one of them is this symbol here, the ampersand. So that's how you form a conjunction in R. We said that here, the way you do it, the way you denote it in logic is use this. But in R, that's not how you do it. You use this symbol. So we are going to be working with some data from the UCI data repository, which I might have shown you earlier. I'll just remind you now. So this is the UCI, I think it's the University of California at Irvine, machine learning repository. There are many data sets there. We're going to be dealing right now with bank marketing data set. They have a data set description, which you can click on. And I guess I'm already there. This is this one, where it describes the data. And you can also click here, and you can see the data. And I want you to download this one here, bank.zip. And then what we need to do is, so I actually called it, it's not called bank data UCI, it's just called, I think, bank. Inside the zip file, I think it's called bank.csv. But I renamed it this. And then this is the way you can read it. Now this is actually not the right way to read it, and we'll see the better code for this in a minute, because this data is not comma separated data. So it's called, the ending on it is .csv, so you would think that it was comma separated values, but actually it's not. It's semicolon separated, so it won't, if you just use this command here, this is for CSV data, and it's not, so this won't work. But I'll show you the way to do it in the next slide. Then after we read it, we're going to give it a name, DF for data frame, and then we're going to convert it to a data frame. We're going to make sure it's converted to a data frame. We're going to check the names of the variables. We're going to view it, and this is another way to view the data. We can use this print statement, and specifically one for data frames, which makes it, you could just use print by itself, but if you do this, it kind of looks cleaner and works better. And we're not going to look at the whole data frame, we're just going to look at the head, because otherwise it would be too big. And then we also want to look at the age variable. There's an age variable in this data set also. This is not the data set we were working on before, but there's also an age variable in this data set. And then we're going to try a command like this. I'm sorry. So there's an age variable here, and we're going to do a statement like this. We're going to say df of age is greater than 30. So what is this going to produce? Well, we already saw what this produces. This is going to produce a Boolean vector. In this case, I'm going to cut it off because I'm only going to look at the head. But basically, this would be a long Boolean vector for every row of the data frame. So each time age is less than 30, it will be true, and for each row where age is not less than 0, it will be false, just like before. Okay, actually I'm going to stop this video here, and I'll come back to this.